let's start with the next chapter. The next chapter is Kinetic Theory of Gases. Okay, and once again, let's revise the ideal gas laws. Okay, so what are they? So we know Boyle's law. Boyle's law says that PV equals to constant at constant temperature. Okay, PV equals to constant at constant temperature. That means if you take that V on the other side or P on the other side, then what do you get? Pressure and volume, they are inversely proportional to each other at constant temperature. Okay, and if you want to plot a graph of them, okay, pressure versus volume graph or volume versus pressure graph, so that graph will look like this. The graph will look like like this. Okay, so this is at some temperature, let's call it at temperature T1, at temperature T1. Okay, suppose 1000 Kelvin or something like that. Then it will look like this. This is suppose at 2000 Kelvin. So because this is pressure versus volume graph, okay, this is pressure versus volume graph. Because temperature is constant here, this is suppose at temperature T2. So these are known as isotherms. Okay, these are known as what? Isotherms, because temperature is constant, right? So this is pressure versus volume graph at constant temperature. Okay, next you have Charles' law, which says that volume is directly proportional to temperature if pressure is constant. Okay, then there is Gay-Lussac's law, so which says that pressure of a gas is directly proportional to temperature if volume is constant. Okay, and then next is the Avogadro's law, which says that at the same temperature and pressure, equal volume of all gases will have equal number of molecules. Okay, so Avogadro's law says that at same temperature and pressure, equal volume of all gases will have equal number of molecules. Okay, so at equal volume, pressure, temperature, right, they will have equal number of molecules. Okay, so this is Avogadro's law. So now, all right, so 1 mole, so Avogadro defined a quantity called as a mole. 1 mole of a gas has volume equals to 22.4 liters at STP, okay, standard temperature pressure, which is 0 degree Celsius, and temperature is what? 1 atmosphere, and the number of molecules are 6.022 multiplied by 10 raised to 23. Okay, so Avogadro says that number of molecules are same if P, V and T are all same for two gases, right? Okay, this thing is clear? Yes, no? If pressure, volume, temperature of two gases, let's say you have gas A in one container, gas B in another container, the volume of two containers is same, okay, the pressure is same and temperature is also same, then they will have what? Equal number of gas A molecules and equal number of gas B molecules. Or number of molecules of gas A is equal to number of molecules of gas B. This is clear? All right, good. So then if we combine these laws, okay, what do we get? We get the ideal gas law, that PV by T is a constant for a given quantity of gas. Okay, so if we combine the Boyle's law, Charles' law, Gay-Lussac's law, we get the ideal gas law, that PV by T is a constant for a given quantity of a gas. Okay, and then now this constant is directly proportional to temperature. Oh, what did I say? So we can move this temperature on this side. So PV would be equal to some constant times temperature, and that constant turns out to be equal to Nr. Okay, it turns out to be equal to Nr. Okay, so the temperature is measured in kelvins, that's the SI unit, right? All right, so temperature is measured in kelvins. Okay, so this derivation we have seen in the last chapter, right? Kind of derivation. right? So PV is equal to nRT is the ideal gas equation. So ideal gas law says that PV by T is a constant for a fixed quantity of gas, okay? And suppose there are n number of moles of a gas, then if you take this T on this side, so okay, what I mean to say is PV by T is constant for fixed quantity of gas, and that quantity of gas would depend on what? Number of molecules, right? Okay, so if number of molecules is more, that means quantity of gas is more. So PV by T is proportional to what? Number of molecules in gas. Okay, that means number of moles, you can say, right? And then you can move this T on this side. So PV is proportional to NT, and the proportionality constant between them is R. R is called as universal gas constant. Okay, R is called as what? Universal gas constant. So PV is proportional to, you can say, NT, and proportionality constant between them is R. R is the universal gas constant. I guess its value is 8.3 something, 8.314, something like that. Okay. All right. So this is ideal gas equation, which we all know. Okay, and we need to remember it. Okay. Next, now this is not explicitly mentioned in the syllabus, but I am just taking it. Dalton's law of partial pressures, because it's not much, okay, and pressure of ideal gas is there in the syllabus. So okay, this is not explicitly mentioned and it's not much of a topic. I mean, it's not huge topic, so I'm just taking it. Okay, it won't take any time. Okay, so Dalton's law of partial pressures says that total pressure exerted by mixture of ideal gases is equal to the sum of partial pressures, okay, exerted by constituent gases if they occupy same volume occupied by the mixture. So what does this mean? So suppose you have this container, okay, and there are n number of gases, okay, gas A, gas B, or gas 1, gas 2, gas 3, so on and so forth. So there is mixture of gas, okay. So P1 is pressure exerted by gas 1, okay, P2 is the pressure exerted by gas 2, P3 is the pressure exerted by gas 3. So for example, suppose there were n1 number of moles of gas 1 only in the container, and the pressure due to that one could be what? Suppose P1, okay, and there is nothing else, okay. So pressure due to gas 1 is P1 if there are n1 number of moles of gas 1. Pressure due to gas 2 would be P2 if there are only n2 number of gas 2 and nothing else, okay. Pressure due to gas 3 is P3 if there is only n3 number of moles and nothing else, okay. Then if you combine them all, if you add n1 number of moles of gas 1, n2 number of moles of gas 2, n3 number of moles of gas 3, and you mix them in the same container, then the total pressure due to all of them is just sum of P1, P2, P3. This thing is clear? Yes, no? Okay. This is the Dalton's law of partial pressures. Yes, is it clear? Yamini? Yamini, Nikita? All right. Okay. So then, now, see, these laws can be derived using a theory called as kinetic theory of gases. Okay, so all the gas laws can be derived using the kinetic theory of gases, which we are going to see now. Okay, so there are some assumptions of the kinetic theory of gases. What are those assumptions? A pure gas consists of large number of identical molecules separated by a distance that are great compared with their size. Okay, so what does this mean? That the gas is very rare, okay, and they have identical number of molecules, okay. So suppose you take some gas, there will be identical molecules, okay, and they are separated by a distance. So distance between molecules is very long compared to what? Size of the molecules, okay. Distance is much more compared to what? Size of the molecules, okay. Then the gas molecules are constantly moving in random directions. with distribution of speeds. Okay, so gas molecules are continuously moving in random directions. Okay, so they are not at all steady. So suppose there is some gas over here, gas molecules move here and there, so completely random directions, they will move in completely random directions. Okay, so next, the molecules exert no forces on one another between collisions. So suppose a molecule is here, a molecule is here, they are moving like this. Suppose one is moving in this way, another one in the other way. So between the collisions, they don't exert any forces onto each other. Okay, so we are neglecting any intermolecular forces, right? Because distance between them is so long. Okay, so in last chapter we learnt about the cohesive and adhesive forces. So they will come into picture when the separation between them is so small, okay, very small, of the order of 10 raised to minus 9 meters. But now the distance between molecules is very long, okay, very large compared to their sizes, and therefore the intermolecular forces will not come into picture. So you are neglecting them. Okay, right, this thing is clear? Yes, no? Okay, good. And then the collisions of molecules with walls of the container are elastic. So whenever these molecules collide with the wall of container, the collision is elastic collision. That means they will rebound with the same speed. Okay, the collisions with wall of the container are the cause of pressure. Okay, so if there is some pressure in a container, so suppose this is a container, right? This is a container and it contains some gas. Okay, there is some gas in this container. So these gas molecules are moving in random directions and they collide with the walls of container. So these collisions are cause of the pressure. Okay, so that's what the kinetic theory of gases say, right? Okay, and then there is a definition. We'll talk about this in more detail later, but for now let's define the mean free path. So what is this? So suppose this is some gas molecule and it moves from here to here, then it collides with some other gas molecule at this point. Okay, so from here to here it traveled freely, okay, up to the distance of, let's say, lambda 1. Then its path changes. So suppose it moves in this direction. Okay, earlier it moved like this, then because of the collision its path will change, right? And it moves in this direction. Here it encounters another collision, okay, and then its path changes again. Here it encounters another collision, again its path changes, something like this. So then now between two successive collisions, suppose it traveled distance lambda 1 in first two successive collisions, in next two it traveled distance equal to lambda 2 freely, okay, in next two it travels distance equal to lambda 3, so on and so forth. Okay, so lambda 1 is distance between first and second collision, lambda 2 distance between second and third collision. So then what is the mean free path? So this is known as free path. Okay, so if you just take average of all those free paths, so you will get mean free path, right? Mean of the free paths is known as mean free path. This thing is clear, everyone? Right? Okay, so this is mean free path. After that, let's talk about the pressure due to an ideal gas. So suppose there is some gas in this container and we know that it will move in random directions. So now just consider a molecule which is moving in x direction. Okay, so suppose this is x direction, then this is y direction, and then one would be z direction, right? So this is x, y and z, like this. Okay, so then now suppose m is mass of each molecule. So there is only one kind of gas, okay, in this container. There is not air, there is only one kind of gas, let's say hydrogen, oxygen, okay, some gas is there. So then suppose one molecule, it's moving with a speed Vx in x direction, okay, m is its mass, so its momentum would be what? M times Vx, right? So suppose it collides with this wall, okay, it collides with this wall and it rebounds. So as we discussed, the collision would be what? Elastic collision, and wall is very heavy, okay, so it will just bounce back with the same speed, right? The gas molecule will just bounce back with the same speed. So when molecule rebounds, the change in momentum of the molecule will be equal to what? Final momentum minus initial momentum, that is minus mvx minus mvx, that is minus 2 mvx, right? This is change in momentum of gas molecule. So now this much momentum is imparted by the wall to the gas molecule, okay, and by the Newton's third law we can say that change in momentum of the wall, okay, the momentum imparted by the gas molecule to the wall would be equal and opposite. So how much that would be? So that is 2 times of mvx, okay. Is this thing clear, everyone? Right, okay. After that, now suppose L is the length of this cubical container, okay. What would be the time between two such collisions? Two such collision means, suppose the gas molecule is just traveling freely, okay, to and fro between these two walls. So if there is no collision between this gas molecule and other gas molecules, then what would be the time between two successive collisions between this wall and the gas molecule? So the distance to be traveled is what? L plus L, 2L, okay, and its speed is Vx. So the time between two collisions would be equal to what? 2L divided by Vx, right? Time between two collisions would be 2L divided by Vx, okay. And therefore now you can just divide this change in momentum by this time. So force exerted by molecule on the wall would be equal to what? Just change in momentum of wall divided by time between two collisions, okay. So that is force exerted by one molecule traveling in x direction onto the wall, right? So if you just put this 2 times of mvx here divided by 2l by vx, okay, this 2 will get cancelled, vx will go in the numerator, so it will be m times vx square divided by l, okay, it will be m times vx square divided by l. So this is force exerted by one gas molecule onto the wall, okay. So then what we can say is pressure exerted by one molecule on the wall is just, let's say, px is equal to fx divided by a, area of the wall, and area of the wall is l square, okay, area of the wall is l square, right? So therefore what is L times L square? It is the volume, okay, it's L cube, it's the volume of the container, and therefore pressure in x direction due to one molecule which is traveling in x direction only, it is m times vx square divided by v, okay. But this vx square is what? Vx is what? It's speed, and this capital V is the volume of the container, right? This thing is clear? Yes, no? Pressure due to one molecule. Okay. So then for n molecules, what would be the pressure? So suppose speed of first molecule is v1x, speed of second molecule is v2x, speed of third molecule is v3x, so on and so forth. So then pressure due to first molecule would be equal to what? M times v1x square upon v. Pressure due to second molecule would be equal to m times v2x square upon v, okay. Pressure due to third one would be m times v3x square upon v. So you just add up the pressure due to all molecules and you get total pressure in x direction, right? So out of that you can take m by v common. Okay, you can just take m by v common. So pressure would be equal to m by v multiplied by v1x square plus v2x square plus v3x square, so on and so forth up to vnx square. And then what we can do is we can just multiply and divide by n. Okay, we can multiply and divide this thing by n. So what is n? N is total number of molecules. Then what do we get? So if we multiply by n to the mass, this is number of molecules multiplied by mass of one molecule. Okay, so this is total mass, and total mass divided by volume is what? It's the density, right? Total mass upon volume is what? It is the density. Okay, so therefore you get Px is equal to rho times v1x square plus v2x square plus so on and so forth up to plus vnx square divided by n. Okay, is this thing clear? All right, then after that, so what we can say is, this is, suppose you take square of the speed of first molecule, then second molecule, okay, up to nth molecule, and you take average of that. Okay, so you are taking average of that, average of the squared speed. Okay, so this is average of the squared speed in x direction. Okay, so this thing is rho, and this is average of the squared speed, squared velocity. So this is known as mean square velocity. Okay, average of the speed square is known as mean square velocity. Okay, so then, so this is just for x direction. You take it for y direction and z direction, then you will get what? So you have this relation, no? V bar is equal to Vx bar plus Vy bar plus Vz bar. Okay, or you can say Vx into I cap plus Vy into j cap plus Vz into k cap, right? Okay, so we know this from vectors. V bar is equal to Vx into I cap plus Vy times j cap plus Vz times k cap. Therefore V square would be equal to what? Vx square plus Vy square plus Vz square, right? This thing we know. Okay, so if we just make use of this, so Vx square bar is the mean square velocity in x direction. Similarly, Vy square bar would be mean square velocity in y direction, and Vz square bar would be mean square velocity in z direction. And if you just take this equation and put bar on top of these, that means average, okay, the mean square velocity would be just sum of what? Mean square velocity in x direction plus mean square velocity in y direction plus mean square velocity in z direction, right? Okay, so this thing is clear? Yes, no? Okay, and after that, see, in the we believe in the justice, right? Okay, so just kidding. We believe in the what do we say? The symmetry, right? So if you just employ symmetry here, okay, because molecules do not have any preferred direction of movement. Okay, molecules do not have any preferred direction of movement, so same number of molecules would be moving in x direction, y direction and z direction at any given time. Okay, so mean squared velocity in x direction would be equal to mean squared velocity in y direction, and it would be equal to mean squared velocity in z direction. Okay, if molecules are moving randomly, then you can say that the number of molecules which are moving in x direction at a particular time, okay, would be same as that of number of molecules moving in y direction, and would be same as that of number of molecules moving in z direction, and the distribution of speeds would also be equal in all three directions because they don't have any preferred direction, right? Is this thing clear? So what we can say is mean squared velocity in x direction is equal to mean squared velocity in y direction, and it is equal to mean squared velocity in z direction, and it is equal to 1/3 of this v bar square. Okay, sorry, 1/3 of v square bar. Is this thing clear, everyone? Right. Why 1/3? Because you can just say that since vy square bar is also equal to vx square bar, vz square bar is also equal to vx square bar, so I can just say that this is just vx square bar plus vx square bar plus vx square bar. So 3vx square bar is equal to v square bar, right? And take that 3 on other side, so you get vx square bar is equal to what? 1/3 of v square bar. Okay, and this v square this v square bar, it is written as vrms square. Okay, vrms square, we'll see what is vrms. Okay, and therefore the average pressure in any direction is equal to what? It is equal to rho times vx square bar, but then we know that vx square bar or vy square bar or vz square bar, it's equal to what? 1/3 of v square bar. Okay, and this thing is called as what? vrms square. Okay, so here see, we can define root mean square velocity. So what is that? So you have mean of squared velocity, okay, v square bar, and you take square root of that, so that is called as root mean square velocity. So basically what that is speed of first particle square plus speed of second particle square plus so on and so forth up to speed of nth particle square. Okay, because you have v square bar, okay, v square average, that means you are taking v1 square plus v2 square plus v3 square, so on and so forth up to vn square, and you are dividing that by n, right? This is average of v square. Okay, v1 square plus v2 square, so on and so forth up to vn square divided by n, and then you take square root of that. So if you take square root of that, you get vrms. So this is called as, so this v square bar is called as mean square velocity, and you take square root of that, so that is called as root mean square velocity. Okay, so root of mean square velocity, right? So vrms is square root of mean square velocity. Okay, that is v1 square plus v2 square, so on and so forth up to vn square divided by n. Okay, so then this thing can be written as what? So if you just take here square of both sides, so vrms square would be just equal to what? V square bar. Okay, so this v square bar is equal to vrms square. Okay, so this is just definition, right? So we need to remember what is vrms. V root mean square speed or root mean square velocity is square root of v1 square plus v2 square plus so on and so forth up to vn square divided by n. Okay, so then what do you get is pressure is equal to 1/3 of rho multiplied by vrms square. Okay, you get this equation, and is there any doubt in this? Yes, no, no doubt, right? Okay, so we need to remember this. Okay, very good. We need to remember this expression. Okay, and also I took the derivation because it gives some insight, okay, how different parts work, right? Now after that, so then next we will talk about the pressure and kinetic energy of gas, the relation between them, the pressure and kinetic energy of a gas. Okay, so see, we have just seen P is equal to pressure of a gas, okay, is equal to 1/3 of rho into vrms square. Pressure due to a gas is 1/3 of rho is density multiplied by vrms square, right? So density can be written as what? Total mass upon volume, and suppose there are n number of particles of a gas, then what can we say? That the mass is equal to n multiplied by mass of one molecule. Okay, so density can be written as what? N times N is total number of molecules, N times mass of one molecule upon volume. This is the density. Okay, density is mass upon volume. So what is mass? It is mass of gas, it is mass of one molecule multiplied by number of molecules, right? So therefore density is number of molecules multiplied by mass of one molecule divided by the volume. Okay, so then what you can do here is, see, you can take this m and you can multiply that with VRMS square. Okay, and then see the adjustment, then you multiply that with half, so that means you have divided by 2, so you multiply by 2. Okay, and then what you do is, okay, so this VRMS square can be written as what? V1 square plus V2 square plus V3 square, so on and so forth, up to Vn square divided by n, right? What is VRMS square? It is V1 square plus V2 square plus V3 square, so on and so forth, up to Vn square divided by n. And then that n and n gets cancelled out. So now you can see what is this thing, what are you left with? So here outside you have 2/3 of volume, that means volume is denominator, volume is in denominator. Okay, 2 by 3V, and in multiplication with that what remains is half of m into V1 square plus half of m into V2 square plus so on and so forth up to plus half of n m into Vn square. So what is this thing? This is kinetic energy of first molecule, this is kinetic energy of second molecule, plus so on and so forth up to plus you have kinetic energy of nth molecule. So if you add up the kinetic energies of all molecules of a gas, what do you get? You get the total kinetic energy of a gas, right? What do you get is the total kinetic energy of a gas. Okay, so you replace this thing by Ke, kinetic energy of gas. Okay, and then this is a formula. So if you like, you can just move pressure, volume on that side and this 2 by 3 factor on the other side. So kinetic energy of gas is just equal to 3 by 2 times pressure into volume. Okay, is this thing clear, everyone? Kinetic energy of a gas just equal to what? 3 by 2 times pressure into volume. Yes, is the formula clear? All right, so this is how it comes. Okay, after that, next let's talk about the pressure and temperature. Okay, so then we know that PV is equal to nRT. Okay, this is ideal gas equation. So in place of PV we substitute nRT, right? So what do we get? Ke is just equal to 3 by 2 PV and PV is equal to nRT, so it is 3 by 2 nRT. Okay, right? And then we remember this from the last chapter. What is R? R is just product of Na and Kb. Okay, what is R? The universal gas constant is product of, just remember this, universal gas constant is product of Na and Kb, right? Okay, so this thing similarly can be written as, okay, see, universal gas constant is Na times Kb, and the number of molecules, number of moles can be written as what? Total number of molecules divided by Avogadro's number. Okay, N can be written as total number of molecules divided by Avogadro's number, right? What is number of moles? Total number of molecules in a gas divided by number of molecules in 1 mole of gas. Okay, so you just substitute that here. So N is equal to what? N is equal to N divided by Na, and what is R? So R is equal to Na multiplied by Kb, so that Na gets cancelled out. Then what do you get? 3 by 2 N times Kbt. Okay, so kinetic energy is also equal to 3 by 2 N times Kbt. Is this thing clear? Right? Okay, so then this is for N number of molecules. Okay, this is for N number of molecules. So average kinetic energy per molecule. For one molecule, just put n equals to 1. Okay, just put this n equals to 1, so it will be 3 by 2 kBT. So this is how we get average kinetic energy per molecule of a gas, and that's equal to 3 by 2 kBT. Okay, that's equal to what? 3 by 2 kBT. Okay, this is clear, right? Everyone? Okay, good. All right. So this is also law of equipartition of energy, but we'll talk about that later. Okay. After that, next we derive the relation for root mean square velocity. Okay. So we have kinetic energy of n moles of a gas is equal to what? 3 by 2 nRT. Okay. We have just seen it here that K is equal to 3 by 2 nRT. So if you use that, what is kinetic energy? It's just sum of kinetic energies of all molecules. So half of m into v1 square plus half of m into v2 square, so on and so forth, up to half of m into vn square. This is total kinetic energy of gas. And if you take 1 mole, if you take n equals to 1, then this is 3 by 2 RT. Okay, kinetic energy is 3 by 2 RT, right? And then what you do is, see, on left hand side, if I multiply and divide by Na, okay, I am dividing by Na and I am multiplying by Na. So what do I get? So I will take half m common and I am multiplying and dividing by Na. So v1 square plus v2 square plus so on and so forth up to vn square divided by n, because these are total number of molecules. We have taken 1 mole, so number of molecules is Na. So this is squared velocity, okay, of first molecule and second molecule and so on and so forth, divided by what? So what you are doing is you are taking average of the squared velocity. Okay, that is root mean square velocity square. What is this thing? This is root mean square velocity, let me say RMS velocity square. Okay, this is RMS velocity square, right? And then here what do you have? You have number of molecules in 1 mole Na multiplied by mass of 1 molecule. Okay, so what is this thing? So this thing is molar mass or molecular weight. Okay, so this thing is molar mass or molecular weight, right? So this is capital M. Okay, small m is what? Mass of 1 molecule. Na is total number of molecules in 1 mole. So this is molar mass, right? So therefore what do you get is, you get half of capital M multiplied by VRMS square is 3 by 2 RT. You cancel out the 2 and 2 and move that M on other side. So you get VRMS square is equal to 3 RT upon M. So what would be VRMS? VRMS is square root of 3 RT divided by M. Okay, VRMS, the root mean square velocity, is just square root of 3 RT divided by M. Okay, is this thing clear? So let's just use PV equals to nRT, right? If you move this volume on other side, so you get P equals to nRT divided by V. Okay, so there are n number of moles. Okay, and then if I just multiply and divide this, by molecular weight, okay, so, or let's say n number of moles are there, right? So n can be written as what? Okay, if I just multiply and divide this by molecular weight, okay, then I get m times n times RT upon this thing, right? I am multiplying by molecular weight, I am dividing by molecular weight. So what is this thing? This is the density, right? What is this thing? This is the density, right? Because this is total mass. Okay, n moles multiplied by mass of 1 mole, right? N mole multiplied by mass of 1 mole is the total mass of the gas. Okay, so mass upon volume is density. So you get this formula, pressure is equal to rho RT by M. Okay, you get another formula, this is very handy. Pressure is equal to what? Rho RT divided by M. Okay, so we can derive it this way, we can derive it from the equation of kinetic energy. But is this thing clear, everyone? Okay, so this is not any separate, I mean, this is just a handy formula. Okay, so I will just say a handy formula. Okay, relation between pressure and density. Okay, but you might say there is another relation. What is pressure? Pressure in terms of density. P is equal to 1/3 of rho into V RMS square. Okay, that is there, but this is another handy formula. Okay, so in some problems this would be more useful. All right, so then let's talk about let's see some problems based upon these things. Let's see this one. The temperature of a gas is minus 50 degrees Celsius. To what temperature the gas should be heated so that the RMS speed is increased by 3 times? Okay, so suppose RMS speed is V1, okay, at 50 degrees Celsius, minus 50 degrees Celsius. Then what would be V2? It is increased by 3 times, means it would be V1 plus 3 times V1, right? So it is 4V1. Yes, no? Right. And then you want to find it out. Okay, at what temperature? No, you want to find out at what temperature it will be this thing. Okay, V2 will be 4 times of V1. So you know this. So we know that Vrms is equal to what? Vrms square root of 3 RT by M. Okay, this is the formula. So if M is same, R is same, R is anyway same. Okay, so it's directly proportional to square root of T. So therefore you can say V2 by V1 is just equal to square root of T2 by T1. Okay, or T2 by T1 is equal to, just take square on both sides. So it is V2 square, V2 by V1 square, V2 by V1 square. That is V2 is 4 times of V1. So this is 4 times of V1. So that V1 gets cancelled out. So it is 4 square means 16. So T2 by T1 is just equal to 16, and therefore T2 is 16 times T1. But what is T1? So it's minus 50 degrees Celsius. We have to take it in kelvins. So it is 16. So minus 50 plus 273. Minus 50 plus 273. Okay. Let's forget about 0.15, right? So 273 minus 50 is 223. Okay, 223 times 16. How much is it? 223 times 16. Tell me. 3568. Okay, so it is 3568 kelvins. Okay, so is there such an option? It's not there. So that means we need to subtract 273 from that. So subtract 273 from this. What do you get? I will just subtract 278. Oh, sorry, 268. So it will become what? 3300, and I need to subtract 5 more because I wanted to subtract 273 in all. So 3300 minus 5, so 3295. Okay, so that's my answer, right? So this is simple. Yes, no? All right. So let's see next one. A given sample of an ideal gas occupies a volume V at pressure P and absolute temperature T. Okay, by the way, this one was from NEET 2023. Okay, this is now very dark, so you can't see that. Yeah, so you can see that, right? So it is from NEET 2023. A given sample of an ideal gas occupies a volume V at a pressure P and absolute temperature T. The mass of each molecule of gas is small m. Which of the following gives the density of the gas? Okay, tell me. So now we have just seen this. Okay, so we have just seen this formula. So pressure in terms of density, P is equal to what? Rho RT by M, right? Okay, remember this formula, pressure is equal to rho RT divided by M. Okay, so now mass of each molecule is small m. This is given, but this is molar mass. Okay, this is molar mass. What we can do here is we want to adjust mass of each molecule here. So what we can do is we can write this thing as Avogadro's number multiplied by mass of each molecule, that is molar mass, okay, or molecular weight. And then there is no R in the options 2, so that means we need to write R as the product of Na and Kb. Okay, Na times Kb. So Kb is just written as K sometimes, right? So let's write R as Na times Kb, and then you have T here. So Na gets cancelled. Okay, Na gets cancelled. So you get rho times Kbt upon small m is pressure, but you want density of gas, so just move these things on other side. So you get density equals to Pm divided by Kbt, right? So this is the answer. So it is option B, right? This one is clear, everyone? Okay, so if we remember this formula, it becomes easy. All right, good. Let's see next one. Two vessels separately contain two ideal gases A and B at same temperature. So two different vessels, same temperature. The pressure of A being twice as that of B. Under such conditions, okay, let's first write PA is equal to 2 times of PB. Under such conditions, the density of A is found to be 1.5 times of density of B. Again the same formula, right? So pressure is equal to rho RT by M. Okay, that means rho is equal to Pm by RT. Okay, so the ratio of molecular weight of A to B is, okay, so we want ratio of molecular weights. So move molecular weight on other side. So what do we get? Rho RT by P, right? Molecular weight is rho RT by P. Okay, so just take the ratio of them. So MA is to MB would be rho of A R times T divided by pressure of A, and dividing by this thing is equal to multiplied by its reciprocal. So P by rho RT, but this is for B, right? And then RT gets cancelled out. Okay, RT gets cancelled out. What is ratio of the densities? So this is just rho A by rho B and rho A by rho B, and in denominator you have PA by PB. Okay, I'm just taking this PB in the denominator because this ratio is given. Okay, so PA is equal to 2 times PB, or we could cancel it here also. So PA divided by PB is 2, right? So PA by PB is 2, and what is rho A by rho B? It is 1.5. So this thing is equal to 1.5 divided by 2. Okay, 1.5 is 3 by 2. So 3 by 2 by 2 means 3 by 4. So that's the answer. Right, it's option B. Sorry, option D. Right, this is simple. Okay, so I particularly like this chapter because most of the questions are like this. Just some adjustment, right? No more, I mean, no substitution of large values, etc. No lengthy formulae. Okay, let's see next one. In the given VT diagram, what is the relation between pressure P1 and P2? Tell me which one is greater. In this diagram, volume versus temperature, P1 versus P2. Tell me which one would be greater. Okay, option A, right? Okay, so everyone says option A. Okay, so PV is equal to nRT is your formula. Sorry. So what you can say is V is directly proportional to temperature, but V is equal to nRT, or let's use for 1 mole RT by P. Okay, so if pressure is more, volume would be less at the same temperature. And here for the case of P1, at same temperature, you take same temperature, right? Let's take same temperature. Okay, so here at this temperature, the volume for this graph, volume in this graph is lower compared to that of the second graph. Okay, so that means pressure P1 would be more. So P1 is greater than P2. Yeah, that's option A. Okay, so very simple question. Okay, it is from NEET 2013. All right, let's see next one. At 10 degrees Celsius, the value of density of a fixed mass of an ideal gas divided by its pressure is X. At 110 degrees Celsius, this ratio is. Okay, tell me. At 10 degrees Celsius, the value of density of a fixed mass of gas, density divided by its pressure is X. Okay, so again let's use the formula. So what is pressure? Rho RT by M. Okay, or density is PM by RT. But you want, what do you want? Density divided by pressure. Okay, so density divided by pressure means take pressure on that side. Okay, so density is equal to PM by RT. Density is PM by RT, and you want density by pressure. So density by pressure would be what? Let's say, okay, density by pressure, this thing is X, no? So let's say this is X. X is equal to density divided by pressure, so that is M by RT, M divided by RT. So it is just inversely proportional to temperature, right? So at 110 degrees Celsius, this ratio is, okay, so initially the ratio is X. At 110 degrees Celsius, what will be this ratio? So we can just say X dash divided by X would be equal to what? T by T dash. Okay, X prime upon X is equal to T by T prime. Why? Because X is inversely proportional to temperature. Okay, right? X is this ratio, density by pressure, and it is inversely proportional to temperature. Okay, and therefore now you can just put the values and take X on that side. So we'll take that. So T is, initial temperature is 10 degrees Celsius. Okay, but then you need to convert it to kelvins, right? You need to convert it to kelvins because this temperature is in kelvins. Okay, So it is 10 degrees Celsius means 273 plus 10, and T dash is what, 273 plus 110. Okay, and then move x on other side, so you get x prime equals to, this is 283 divided by what, 383 times x, and that's the answer. It is option B. Right, this one is clear. Okay, very simple question. Okay, let's see next one. The equation of state for 5 gram of oxygen, okay, at pressure P and temperature T when occupying a volume V will be. Okay, so they are just asking about ideal gas equation for 5 gram of oxygen. So what are the number of moles here? Tell me. Mass of gas divided by m. Okay, molar mass of molecular weight, right? What is the molecular weight of oxygen? This is not 59, okay, this is 5 grams, right? What is molecular weight of oxygen? 32 grams, right? Okay, so then this is 5 by 32. So what would be the answer? PV equals to nRT. N is 5 by 32. So PV equals to 5 by 32 RT. So this one is very simple question, right? Okay. This is from, yeah. Okay, you are liking that question. Good. All right. Let's see next one. 3 containers of same volume contain 3 different gases. Okay, the masses of molecules are m1, m2, m3, and a number of molecules in their respective containers, okay, in 3 containers is n1, n2 and n3. The gas pressure in containers are p1, p2 and p3 respectively. All the gases are now mixed and put in one of these containers. The pressure P of the mixture will be, okay, tell me. So this is just direct question based upon the Dalton's law of partial pressure. Okay, you have gas A in one container, gas B in second container, okay, gas 1 in first container, gas 2 in second container, gas 3 in third container. The pressures are P1, P2, P3. If you mix it all, then the pressure becomes P. So P is just equal to what? P1 plus P2 plus P3. Okay, that's it. Right? This thing is clear? Okay, good. But they haven't explicitly mentioned the Dalton's law of partial pressure. Okay, but they have mentioned the pressure due to ideal gas. Okay, so I guess you might have seen this in chemistry also. Is it there, Dalton's law? It's there, right? So you don't need to remember anything extra. It's there already. Okay, let's see next one. Increase in temperature of a gas filled in a container would lead to, tell me. Decrease in intermolecular distance, increase in its mass, increase in the kinetic energy, decrease in the pressure. Which one is correct? So we have learned that kinetic energy of a gas is equal to 3 by 2 PV or 3 by 2 nRT, right? So if you increase the temperature, what will happen? The kinetic energy would increase, right? So it is option C. This is very simple. Yes, no. This is from NEET 2019. Okay. So the molecules of a given mass of a gas have RMS velocity of 200 meters per second at 27 degrees Celsius and 1 into 10 raised to 5 newtons per meter square pressure. When the temperature and pressure of gas are respectively 127 degrees Celsius and 0.05 multiplied by 10 raised to 5 newtons per meter square, the RMS velocity of its molecules in meter per second is. So this is simple, right? So molecules have velocity of 200 meters per second at 27 degrees Celsius and 1 multiplied by 10 raised to 5 newtons per meter square pressure. Okay, so this is given, and you are given with another temperature and pressure, and question is what would be the RMS velocity. Okay, so you have RMS velocity, let us just write V only, Vrms is square root of 3 RT by M. So now they have provided temperature as well as pressure, so both things are not required, right? You can make use of only temperature, okay, and pressure is different, so there is no need to get confused over here. We can only make use of temperature only, right? And we can find out the RMS velocity, okay, because PV would be equal to nRT. Okay, so PV would be equal to nRT. If pressure is different, there would be change in volume in such a way that, okay, that the PV would be equal to what? The product of PV would be directly proportional to temperature, right? So don't need to think about the pressure. Okay, so you can make use of V2 by V1. Okay, it's equal to just square root of T2 by T1, and then put the values. So what are the values? The values are T2 is 127 degrees Celsius, so convert it, 127 plus 273, right, divided by, you have 27. Okay, T1 is 27 degrees Celsius, 27 plus 273. Okay, just add it up. So this thing is 300, this thing is 400, 400 by 300, square root of 400 by 300. Okay, so V2 divided by, what is V1? 200. So take 200 on that side. So V2 is just equal to what? 200 times square root of 4 by 3. Okay, that is square root of 400 divided by 300. Okay, so you can take square root of 4, that is 2. 2 times 200, it is 400. 400 divided by root 3 is the answer. Okay, so it is option D. So this one is simple, right? Okay, very simple. Okay, let's see next one. In a vessel, the gas is at pressure P. If the mass of all molecules is halved and their speed is doubled, okay, mass is halved, speed is doubled, then the resultant pressure will be. Okay, so now what formula do we have for pressure? It is 1/3 of rho into Vrms square. Okay, so speed is doubled, so we can say P prime would be equal to 1/3 of rho prime times Vrms prime square. Okay, so that is 1/3 of. Now if mass is halved, what will happen to the density? Density will also become half. Okay, because density is mass upon volume, and they have not given that volume is changing. Okay, so we can just say the density rho prime is equal to rho by 2. So it is rho by 2 times V prime is equal to what? 2 times V. Okay, speed is doubled, so it is 2 times of Vrms square. So then we get half factor from here, and 2 square is 4. Okay, so factor of 4 from here, 4 divided by 2 gives us 2. So this thing would be what? 2 times of 1/3 of rho into Vrms square, that is 2/3 of, sorry, not 2/3, 2 times of pressure. Okay, 2 times of pressure, 2P. Right, this one is simple, very simple. Okay, any confusion in this, Selva Kumar? Anyone? No, right? Okay, good. All right. Then let's see next one. At 0 Kelvin, which of the following properties of gas will be 0? Tell me. Vibrational energy, density, kinetic energy, potential energy. Okay, we saw this kinetic energy is equal to what? 3 by 2 RT. Okay, for 1 mole of gas, it will be 3 by 2 RT. For n moles, it will be n times 3 by 2 RT. So, if temperature becomes 0, temperature is 0 Kelvin, what will be 0? Kinetic energy would be 0. Right? This is clear? Okay, very simple. Right? Okay, let's see next one. Relation between pressure, kinetic energy per unit volume of gas is. So, we had seen this. Okay. What is pressure? Pressure and kinetic energy. So, pressure is equal to 1/3 of uh, rho into V RMS square. Right? We had derived this relation, no? So, it is 2 by 3 or something. 2 by 3 times of E. Yes, no? Okay, if you remember. So, we have derived this relation between pressure and kinetic energy. So, that is, yeah, pressure, kinetic energy is 3 by 2 times pressure into volume. Is it so? So, that question would be, yeah, that's correct. Kinetic energy is 3 by 2 times of PV. 3 by 2 RT means 3 by 2 PV. Oh, they are saying unit volume, no? Right. So, we know that the kinetic energy is equal to what? 3 by 2 RT. Okay. 3 by 2 nRT. Let's say 3 by 2 nRT. So, then we know PV is equal to nRT by ideal gas equation. So, it is 3 by 2 PV, and they are saying unit volume. Okay, so unit volume means V is equal to 1. So, that's why what do you get? E is equal to 3 by 2 P, or you want P, so that will be equal to 2 by 3 E. Right, so this is the answer. Okay, this one is clear. Okay, good. Then let's see next one. According to kinetic theory of gases, at absolute zero of temperature, water freezes, liquid helium freezes, molecular motion stops, liquid hydrogen freezes. Tell me which one is the answer? Which one is the answer? Option C, right? Good. Molecular motion will stop. Okay. So according to kinetic theory of gases, at absolute zero of temperature, molecular motion will stop. Right? So this is simple. All right. So then at constant volume, temperature is increased, then what will happen? Collision on walls will be less, number of collisions per unit time will increase. Okay, collisions will be in straight lines and collisions will not change. Okay, if temperature is increased, that means collisions will increase, decrease, or what will happen? They will not change. Yes, everyone, if temperature increases, what will happen? Speed of molecules will increase. Yeah, so number of collisions per unit time will increase. That's correct. Okay, so as speed increases, what will happen? So suppose you have, consider these two walls and molecules are moving like this, okay, towards that wall, let's say in one dimension only. So if speed increases, that means it will collide more frequently with this wall as well as this wall. Okay, so this is simple. Number of collisions would increase. Okay,